Okay, welcome everyone. Since we're recording, we'll get started. I'm happy to welcome Owen O'Driscoll today for the uh, Air-Sea Interaction from Space webinar series. And he's going to talk about FluxSAR, air-sea heat fluxes from SAR. I'll
All
let you
right.
take it away, Owen.
Thank you very much for the introduction. So I have a presentation here on heat flux retrieval using synthetic aperture radar. I gave a shortened version of this presentation last week at the Ocean Science meeting. So I briefly saw some faces here which were also there, but I promise that there will be some other, hopefully interesting new nuggets of information as well. But to start off with an introduction, so we have these synthetic aperture radar images, which, such as this one, which happens to be one of my favorites, which is located a few hundred kilometers southeast of Washington, DC, on the edge of this cold coastal waters and a much warmer Gulf Stream. So it's at quite an interesting location. And we can also see all sorts of interesting features in this SAR image which relate to its this location. I have a schematic here to illustrate what we're actually observing. So we have our radar, which is transmitting its electromagnetic waves, which travel through the atmosphere mostly unaffected, depending on who you ask. And then it interacts with the small scale waves on the ocean surface. So that is actually what the radar is observing, the scattering from these waves. But it is the atmosphere above which is actually driving this small surface roughness. So indirectly, the ocean has quite a good insight into what the atmospheric wind field looks like. So for that reason, most of the variability that we observe in these SAR images is in fact wind-driven, with a couple exceptions for ships here or there. So that allows us to reinterpret these images in terms of what is happening to the wind field. So we have our cold coastal region with cold winds, which are propagating towards the much warmer waters of the Gulf Stream. And once these cold parcels of air travel over a much warmer ocean, we get this thermal disequilibrium. And in an attempt to reintroduce an equilibrium, we of course get some type of convection. And that is these nice textural features that we can observe. So beyond this SST front, we get these Meili-Bénard type of convective cells, whereas prior to the SST front, where there is a more stable condition, we have not very interesting textures. So the point of this example is the fact that our radar images a lot of atmospheric information, which we can visually observe. But ideally, we would like to quantifiably decode this information into something that is of interest, such as heat fluxes. And that's where our FluxSAR retrieval algorithm comes in, because that's the purpose here. So to very briefly give an overview of what our FluxSAR algorithm does, we take our radar image, subdivide it into smaller vignettes, about 20 by 20 kilometers. So this isn't exactly to scale. And then from these local vignettes, we extract some second order statistics, which we believe are closely related to the second order turbulence spectral parameters. And then we end up with millions of these small vignettes, each with their second order statistics. And we can then co-locate those with a reanalysis flux, for instance, from ERA5 or something else. And because we have so many, we can then learn the average relation between our backscatter variability, which is our second order statistics, and the fluxes of interest. And as I also pointed out at OSM last week, this reminds me of what scatterometers have been doing for decades. But scatterometers learn the relation between average backscatter and average wind field. And we're basically learning the relation between average backscatter variability and average wind field variability parameters. And I think there is a fundamental basis for choosing this approach, because the gold standard for these heat fluxes, which is from in situ sensors, they rely on the temporal integration of some turbulent quantities. With SAR, we can't do that. We can't measure these turbulent quantities directly, but we're sensitive to them. And instead of being able to do a temporal integration, we get this instantaneous spatial overview. So we're in slightly different domains, but they correlate to each other. But we don't have a neat transfer function which lets us go from one to the other. And that's why this empirical methodology is quite convenient. So that's it for the introduction. We have our SAR images and we want to extract fluxes from them by exploiting the correlation of the texture to fluxes. I'll go into a bit more detail now on exactly what type of data we're using and the methods. So for the results I show here, I'm exclusively using Sentinel-1 data from the European Space Agency. Sentinel-1 has a bunch of different radar products, but I'm using two, one of which is these nice continuous SWATs called the interferometric wide SWAT mode, which is primarily acquired over coastal regions or the Mediterranean and North Sea. There's more of these observations over Europe because Europe is paying for this mission and it's seen as the luxurious measurement type. And then for much of the open oceans, they resort to another observation mode, which is called the wave mode. So these are sparsely sampled 20 by 20 kilometer vignettes. Now, these two products have some unique features relating to their polarimetric capabilities, their resolution, etc. But for the purpose here, the only thing of relevance is that they span slightly different instance angles. So we can't necessarily compare one to the other, at least not all the time, and that they are mutually exclusive. So we don't have wave mode in the Mediterranean, and we don't have this interferometric wide SWAT mode over most of our open oceans. But this is the radar data. For our target, as I already mentioned, we're relying on ERA5 to give us fluxes. And if you go to the ECMWF portal, you will find they have some averaged heat flux product. But we want to compare these fluxes to a more instantaneous measurement from our SAR. So in order to make these fluxes more representative of an instantaneous measurement, we take ERA5 state variables, such as SST, air temperature, pressure, etc., which according to the documentation are representative of an exact time stamp, so not an integration. And then we feed these into the core algorithm, which gives us something slightly more instantaneously representative. And this is a bit of a academic conversion because in the end, these hourly average heat fluxes and these instantaneous heat fluxes are strongly correlated. But we do find that manipulating our heat fluxes in this way ends up allowing our retrieval algorithm to learn a lot more geophysical information. So it actually greatly improves our correlation to in situ buoys. So that's our target data. Very briefly, how do we train this relation? So we're relying on relatively standard regression where we have our second order statistics and our ERA5 plus core flux. We're using linear tree-based models so we have a diversity in models, and then for each model type, we also have a diversity in hyperparameters. And all this diversity lets us find or train towards a greater proficiency than we were to if we were to stick to just a single model. But perhaps the most interesting of our training procedure is that we're resampling our training data prior to actually the training itself using so-called successive k-means clustering, which basically creates a uniform distribution out of data where the hyperparameter space of your data probably follows a skewed or a Gaussian distribution. And that has the effect of culling redundant samples. So you'll find that a lot of your radar observations are very similar to other radar observations. And if you train towards this heavily skewed distribution, you will probably only be good for a subset of observations. But using this resampling, we are overweighting towards rare events. So that's quite nice. And then we have a second stage, which I call calibration, but it's probably a poor name. But this is where we're learning the uncertainty of our individual estimates. So on one subset of data, we are training a model to make estimates. And then on another subset of data, we are assessing how well each estimate performs with respect to our reference. And we do that using a so-called conformalized quantile regression. So yeah, that gives us a 95% confidence interval per each estimate. And a nice thing of getting uncertainty estimates in this manner is that we're not a priori imposing a distribution that our uncertainties should follow. So we're not forcing the uncertainties to be Gaussian, for instance. And I've tried to summarize this in this cluttered scatter plot in the bottom, where in the y-axis we have the predicted heat fluxes, and then in the x-axis, we have the range of our confidence interval. And what I would like you to observe is that if we move towards the right along the x-axis, the color changes, which indicates that the errors are increasing or decreasing, depending which way you're moving. So the point here is that we have a metric to assess the quality of our measurement, which allows us to, for instance, select per sensible heat flux magnitude bin a subset of samples which have higher relative confidence than other subsamples. And this allows us to filter out quite some data if we think that the confidence is too low. So this is one way that we can filter out data, which we can use for both our small wave mode vignettes and also for our much larger IW mode vignettes. That's what I refer to as the uncertainty filtering. And for the wave mode vignettes, we also have another type of filtering we can do using predefined classes. So each of the vignettes has a class label attached to it, uh, which is based on a bunch of work from a few years, or yeah, several works over the past few years. So for instance, we can remove scenes which we know are contaminated with icebergs or biological slicks because we assume that the atmospheric information content they carry is either insufficient or is cluttering our signal of interest. So that's was a bit of detail on the methodology. What can we actually do with a model trained in this fashion? Well, for that, I return to my favorite SAR scene where we have this nice SST front, which is on the left. And then using our FluxSAR methodology, we can use the texture of the image on the left to make a sensible heat flux estimate, which is what I'm showing in the center. And of course, this image on the left and in the center are quite similar because the center is based on the image on the left. And then in the right, we have the sensible heat flux prescribed by RF5 for this same location, which happens to be quite similar. So it also identifies a front, but it might be a bit misplaced or perhaps a different magnitude. But in general, this is a situation where things align quite well. I can show, of course, other examples where things don't necessarily align as neatly, such as this atmospheric front leaving the Gulf of Lyon, where we have a sharp high-frequency event, which we can observe in the SAR image. And so if we use this SAR image to infer our fluxes, we can trace this event. Whereas compared to ERA5, there is some phasing issue. So this front is still contained within the Gulf. And were you to look at the time series of this atmospheric front from ERA5, you will find that, in fact, it never reaches the extent that the radar image suggests. So these are two examples. I could continue this whole presentation with a bunch more, which I don't necessarily want to do. But what I would like to point out is that these radar images are incredibly rich in information content. And you can contrast that with the information content of their ERA5, our reanalysis on the right. And basically what we're trying to do with our FluxSAR retrieval is to redistribute ERA5's values by incorporating the information inside this radar image. So we're kind of trying to mix these two different worlds. I can do the same with the latent heat fluxes just to give both equal amounts of attention. But here I'd particularly like to highlight the bottom example where we have these nice orographic winds of the tippy toe of the Italian coast. And we can see in the SAR image that these are two distinct events, or at least two different fronts, whereas Air 5 is prescribing this general region with enhanced fluxes. But if we rely on the SAR image, we can more clearly delineate these two. I can also present these same results in a video if people here prefer video formats. So I have here the weekly average flux estimates over the Mediterranean using these large scenes. And yeah, weekly average is perhaps a bit unfair because basically every pixel is only covered once, because during this epoch, I think there was only one or two satellites operational, and we're only looking at one of the orbits. So there's at least double the data, which I'm not showing. Yeah, we can also look at time series. So this is the same information, but then taking the weekly time series, just to show that using just the radar information, we can really trace what Era 5 is prescribing for this location. And things are even better if we look at sensible heat fluxes. So then we have quite a nice fit where, again, we're only using the radar information trained on a single year, and then we predict the sensible heat flux variability using that. This is all for these large IW scenes. We have the smaller wave mode scenes as well. So I'm showing a similar time series here, representing the weekly average on a global scale for sensible and latent heat fluxes. The extent of the time series is a bit different here because there are some recalibration issues prior to a specific date. But in general, there's a similar degree of a fit. And then on the right is a figure with not a lot of scientific utility, but I like being able to show the fact that we actually have this global coverage with this wave mode for most of the oceans, with the exception of, for instance, the Mediterranean and the North Sea, which you might see are, which is where we have these other samples for other regions as well. So if we don't have this IW mode, we usually rely on wave mode, and near the poles, which I'm not showing, there's a third mode, this extra wide swath, but we haven't used those. Now, ideally, I could compare to something else in addition to Era 5, but as I pointed out at OSM, we don't really have large in situ networks which span the globe, which we could compare to. So we're quite limited in that sense. But I think, in fact, yeah, that should be one of the motivators to get your heat fluxes from a spaceborne system, because as I was just discussing before the start of this presentation, large parts of the world are simply devoid of measurements. So anything is better than nothing. Fortunately, we do have some regions with buoys, in particular near the equator. We have several different arrays. Now, unfortunately, the equator doesn't have as nice seasonal cycle as other parts of the world. But still, when comparing to these buoys, as I do in these figures on the left, we find that the correlation of our FluxSAR estimates compared to the buoy increases with a shorter distance, which is what we would expect. Although at first it trails the buoy Era 5 correlation at long distances. And I think that kind of makes sense because if we're relying on these radar images, they're capturing higher frequencies, which Era 5 doesn't capture. So we have additional sources of potential decorrelation. But then once we get closer to the buoy, the capturing of these higher frequencies starts to pay dividend. So we actually start to equal, and it looks like the slopes are surpassing Era 5. So perhaps on top of the buoy, we would be able to make better estimates than Era 5. So now that you've indulged me in all the nice results, I think this is a good community to also share some limitations. So for that, I have more global maps, but in this case, showing the statistically significant prediction difference between our FluxSAR estimate and Era 5, where I've grayed out areas where the difference is statistically insignificant or where it's quite small. So for some of these regions, we have these buoys near the equator, for instance, and we can try and piece together what is causing the features that we see on these maps. So for instance, near Cape Verde, when looking at the radar images, we can see that there is quite a high frequency of images contaminated with internal waves. Perhaps contaminated isn't the right word if you happen to be studying internal waves, but they're interfering with our estimates. And then in the figure on the bottom, we see something else. So we have gravity waves, some maybe slick, and we're hitting the noise floor. So there's just a lower quality of atmospheric information content present in some of these SAR scenes. And then another location where the buoy was able to identify that we're persistently off was just north of Madagascar, where again, this image in the north shows these strong gravity waves, not gravity waves, internal waves, excuse me. And then we have this image in the bottom, which I'm not exactly sure what it is showing, in fact. So yeah, some regions we just have contaminants, which many of these we've been able to remove using either the filtering with the classification or with our uncertainty, but we still have some additional filtering to do. But fortunately, for most of the world, that doesn't seem to be a major issue. Now, for the IW mode, we have a different set of limitations. So we've only assessed this IW data for particular regions of the world, where in this case, for instance, we've trained using data from the North Sea, the Mediterranean, and the east coast of the North Americas. And we find that this model performs almost equally well in the North Sea as in the North American coast. So that's quite nice. There's a bit of an exception here over the Gulf Stream, but I'd be happy to blame that on issues in coupling coefficients. But then if we look at latent heat fluxes, we find that there's actually a bias. So if we're training on a subset of regions, then we have a positive bias in the North Sea. In the Mediterranean, as I showed before, it doesn't appear as much. And then for lower latitudes, we have this negative bias. So yeah, we have potentially regional biases. And this doesn't appear as much when we're training on the wave mode. So if we have a well-distributed samples to train on, this is not so much an issue, but this could indicate that we need some additional information to transfer if we're training on a single location. So yeah, just for the last point, last scientific point, which is that again, we're not directly observing these sensible or latent heat fluxes, but we are measuring backscatter with the radar, and we're just exploiting the correlation of this backscatter, the variations and the magnitude to these heat fluxes. So we still have to investigate what the limit is of information that we can extract in that manner. But that's simultaneously also an opportunity because we're not constrained to targeting sensible or latent heat flux. We could perhaps also target the constituent components of these fluxes, which are particularly of more interest to, for instance, the assimilation group, or if you're into assimilation, because from my understanding, the heat fluxes are a bit too ephemeral, whereas they need more the state variables. So I've just one example here of a different model, which we've trained on the same data, but now we're targeting the temperature difference between 10-meter atmosphere and the SST. And we get similar performance as targeting sensible heat flux, which makes sense because your delta T is one of the strong indicators of your sensible heat flux. But this is just to show that we can choose to target something else as well, where again, these radar features are quite indicative of a much warmer region, again, over the Gulf Stream next to a much colder region. So just some perspectives before I end the presentation, which I will use a fancy ESA graphic. So this is the timeline of European Space Agency's satellites, where we can see that the first few missions were these SAR instruments, which have flown over the preceding decades. Now, in recent years, we've mainly been using the Sentinel series, which is the workhorse of the European Space Agency's SAR program. And it's in fact only since last year that we've had three of these operational because Sentinel-1B failed prematurely. And it was many years after that failure till we got the next satellite, Sentinel-1C. And I'm not even sure if Sentinel-1D is fully operational yet for the public. So we have more SARs operational now from ESA side than ever before. And in the next few years, we're going to get missions such as Harmony, which could add the complementarity to the SAR observations. There's some other missions which I haven't highlighted here, such as Chimer, which I think I'm now maybe pronouncing correctly or maybe not. And also Rose-L, which is another SAR imager at a slightly different frequency, but perhaps there's similar information content we could retrieve. But perhaps most important of all is this Sentinel-1 next generation, which should provide the continuity for SAR observations beyond 2030. So then we have decades of promised SAR observations, and we already have decades of past SAR observations. So we're really data rich when it comes to this oceanographic SAR observation database. It's a huge archive. So any type of methodology that you can derive using just the SAR data to extract some geophysical parameters of interest more or less instantly unlocks climate level scales that you can analyze. I think that's a good point to end the presentation. So just to summarize, we've developed this retrieval algorithm where we're using the texture in the SAR images to relate to, in this case, RC heat fluxes of interest. We've trained this to match reanalysis on the large scales, which we see that works on a global scale or on a regional scale. Yet still we retain the freedom to capture a whole new range of scales which are absent in reanalysis products. And if we compare this to a limited set of in situ validations, such as from the buoys around the equator, we find what I would call a competitive correlation. And as I just mentioned, all of this is observation-based. So we've constrained ourselves to looking only at Sentinel-1 for a subset of years, but we could potentially expand this to many more years. Now, of course, there's some things from our side which we have to do, like improving the filtering of the data that we're actually using. Some of it happens to not contain useful atmospheric information, so we should be more stringent in how we discard those scenes. And then there's also the question of how far we can push this retrieval, what parameters we are better or worse at retrieving, and what all these limiting factors are. But I think I've been blabbering for long enough now, and maybe these 8-minute OSM presentations aren't so bad. Anyways, thank you very much.
Thank you, Owen. It's great to have this expanded beyond the 8-minute instant talk. Um, Questions? And maybe while people think of questions, I can start by asking about the performance difference between latent and sensible heat. What physics do you think drives that?
Yeah, I'm not sure. I think we could probably get some hints by looking at the bulk flux formula. So if you have anything that is affecting your latent heat flux, but doesn't show up as characteristic textures, for instance, could be whatever, then you kind of break this unique link between your textures and your parameter of interest. And interestingly, if we train on this global data set of wave mode data, that doesn't occur. So I suspect that maybe if we are training on a subset of data, mostly focused on the northern part of the northern hemisphere, the Mediterranean and the North Sea, that maybe we are sort of training towards a shortcut so that our model isn't fully sampling the state space properly, which could cause it to fail under other conditions. But it could also be that there is, for instance, a signal of your Coriolis or of your salinity, which just doesn't imprint itself on the textures. And then including ancillary information might greatly improve your estimates. But that's something we still have to look at. And that's also why we were looking at targeting these state variables. So for instance, if we can target delta T properly, that means we can get a good sensible heat flux. And so we'll just keep going and see how far we can get, I guess.
Thanks. I see that Ryan has his hand up.
Yeah, thanks. This is perhaps a clarification question. I want to understand more the point you made about averaging over an hour of the era 5 data compared to the other way that you said was much better. Yeah.
Yeah, so if you hop on the ECMWF portal, you'll find heat fluxes from era 5. And these heat fluxes are designed to be the average of that hour, either the next or the previous hour from, so it's some sort of a time integral. But in these SAR images, we see something that is like an instantaneous event. So we would like our reanalysis flux to be representative of that event, because otherwise we are introducing this phase delay between what we're targeting and what we're actually observing. And our workaround here is to take era 5's variables, which are for an instantaneous point. So its state variables are SST, pressure, etc. These are variables representative for a specific timestamp, not for the temporal average. And we feed those to core to get a slightly better representation of our fluxes. Now, of course, core is designed to give you a 10 or 20-minute flux average as well. So there's still some averaging that's happening here, but it gives us much better correlation to the buoys, and it doesn't affect our ability to match the fluxes from era 5. So we're just extracting more geophysical information, or we're learning a better extraction of geophysical information. I hope that answers your question.
Yeah, that makes sense. Thank you.
Other questions? Roger.
Yeah, this you mentioned the sort of analogy between the spatial turbulent measurements from the SAR and time series from, say, moored observations. But those are not really, I mean, the analogy makes sense, but I thought as these are, or what I thought of then was, well, they're not quite the same quantities that are being measured in the two cases. And then I wondered, well, has ever anyone thought about ever putting a SAR on a mooring and trying to do the turbulent time series correlation and see how that comes out?
I think they have maybe not a SAR, but I'm sure they have some like stationary radars. So in order to get the SAR part, it has to be moving. Uh, uh, they have some radars on platforms, but yeah, you would need to somehow image your scene, get these high resolution textures. And if you're relying on coastal radars, for instance, I don't think their spatial resolution is sufficient to capture these 100-meter or kilometer scale micro scale turbulent textures. So if there is such a platform where you could get 100-meter scale spatial resolution, then it would be quite interesting to get your time series on a much greater level. And in fact, we're struggling with these buoys, in fact, because not always is there a valid measurement, and then you will have to wait quite long for another SAR observation to come by. And as this graph shows, there's quite a large spatial distance as well. So there's a lot of decorrelation that can happen. So yeah, I like your idea. If you could have them simultaneously, frequently, the more the merrier.
Okay, thanks. Good point about the SAR moving.
So other questions? Maybe I can ask Owen, you're targeting sensible and latent heat fluxes. It People have done a lot of work, including some of your collaborators, with wind and currents from SAR systems, at least one component. Is there any possibility of getting at momentum fluxes or momentum exchange in any way with this sort of
Uh,
approach?
I have a colleague who's doing a PhD on that somewhere around here.
Ah,
So it's a
so
work in progress, and
excellent.
I think there's probably a relation. There was a similar
Mhm,
question at OSM relating to these momentum fluxes. And
mhm.
since we know that stability plays a part in the exchange between your atmosphere and your ocean, I'm sure there's part here that transfers to that question. But yeah, I happen to not be an expert on that.
Thanks. Adria.
Thanks, Owen, for this longer presentation. It was very nice. So yeah, I have a very practical question. Is the FluxSAR available to other people? And I have specific interest around Greenland and all the data there. And in HH polarization, is your model capable to play with HH in polar area, or it will raise some issue there?
So come back to the last question. We haven't tried this in HH. I think your atmospheric signatures should be stronger in VV than in HH, so we might have some issues to that. But we have aspirations to extend what we're doing here to this extra wide swath mode, which is observations closer towards the poles. And I think maybe a bit north of Greenland or surrounding Greenland, you would have more of these. So that's something we want to do, but we don't have yet. It would also be interesting to have some sort of in situ validation we could use to actually assess there if that works. Then for your first question, we don't have any of this publicly available yet. We don't have an operational retrieval, but again, we have aspirations. So perhaps somewhere down the line. Yeah, and I recently submitted something on this to a journal, and then maybe they will ask me to put it online, which I'll do at some point. But ideally, we don't have like a static data set of observations which were made from the past, but that we can continually update it with a new observation. But till now, we've really been trying to squeeze as much information out of the retrieval, make it better, and hopefully soon we can start thinking of making it more operational. Thank you for your questions.
Thank you.
Other questions? Does ECMWF use SAR data in any way in their reanalysis procedure? Do they have access to SAR?
I wouldn't know. uh,
It's
I think they
notoriously
must.
difficult to figure out what they do use, but
Yeah, they must use scatterometers. So
Mhm,
yeah, for an assimilation point of view, it should be possible to some extent. Though I recently heard that they strongly cull the scatterometer information as well, so it's not
mhm.
including all the information. Uh,
Yeah.
so, but yeah, I wouldn't know, unfortunately. But we would like to also try the assimilation game, so to actually incorporate this into
Mhm,
some sort of a reanalysis and then see if it actually pays dividend. And in
mhm,
fact, that would be the best outcome, in fact, because these examples which I'm showing here, the fact that we can match Area 5 or sometimes go beyond Area 5 are just us trying to motivate the validity of
mhm,
retrieving this parameter using radars to hopefully eventually include in some sort of operational product like what ECMWF is producing. So if
mhm.
anyone is in this chat and has interest in playing the assimilation game, please reach out to my email.
I'm struck that there are a whole bunch of people on this call who produce um, sort of satellite-based flux products, Lisan and Juan. And it would potentially be interesting just to compare what's coming out of these different efforts.
Yeah, I've been looking for uh, the updated best flux estimate. I forget the exact name now, but I think there's a promised high resolution flux sort of assimilation product. So I keep refreshing the page, but it's not there yet to compare.
Lisa, go ahead.
Hi, Sarah. Thanks for mentioning it. And actually, and thanks to Owen for the excellent talk. And I really enjoy it because it's opened a new perspective on how to estimate fluxes. We have struggled, I mean, for our group, we've been doing those like Buck formula-based fluxes, and then we struggled about those two ends, two extremes, really high wind speed versus really stable weak wind speed. Your slides showed mostly about the sensible flux pictures. And I just wondering, in your retrieval, because your retrieval is constrained by EI5, so EI5 does not has ability for the high winds, and you probably won't be able to predict from those like machine learning algorithm. So I just wondering, can you show a case like a hurricane? Are you able to predict this like a hurricane strength? And for us, when we use EI5, like our students use EI5 to simulate a hurricane, we have to double the strength of EI fluxes on hurricane speed. So for in that case, how is your algorithm perform? And and also for the stable at high latitude for the Arctic Ocean and high latitude, I see you have large departures from the EI5. So do you think is the EI5 unable to you are not able to constrain from the EI5 or something you need more observations? And then lastly, and your K-mean is pretty linear, you mean non-linear, but not a very like deep learning kind of approach. I wonder if you use more advanced uh, neural network, whether you could do better.
Very interesting questions. Yeah, we've been playing the game of trying to make our retrieval more complicated using some sort of a deep neural network to extract features. We've been playing with variational autoencoders to get this latent space from which we can target our parameters, all to go away from these linear or boosted models. But so far, we haven't had success in surpassing these simple models. And yeah, that could be for several reasons, but yeah, it's not broken, so we're not going to fix that unless something else comes that's much better. Then relating to what you said on Era 5, we would inherit the issues from Era 5 in our product, which yeah, so if, for instance, Era 5's seasonality doesn't make sense, we are learning to match Era 5 seasonality, so we would also inherit that. But what we do see is that when Era 5 is making a prediction which doesn't match the average relation between backscatter and fluxes, such as in this example, we have the ability to deviate from that. So this is on like a single case. We've been asking ourselves the same question relating to the deviations we see in this map, if that could be related to discrepancies on Era 5 side, but we don't know yet. So we've only been able to pinpoint or attribute the errors where we actually have this third validation point from our buoy. So that's something we would like to look into. And then your first question was relating to high winds. I think that would be particularly tricky for a SAR-based product because we know that scattering from, or the scattering that the SAR observes saturates at the polarization level that we're using. So there would be less information content that we could actually use inside our image. But still, one of the examples which I showed here is not of a hurricane, but of a medicane uh, in, uh, in the Mediterranean. Although this is a decaying medicane, so it's not, the winds aren't 50 meters per second, they're much lower than that. But we can already see, for instance, that in the reanalysis, this entire large extent is attributed to be the core of the storm. And if we're relying on the radar textures to represent the flux variability, we can already delineate that the core is much smaller and that we have enhanced fluxes trailing the medicane, which I believe is where you might have more or less turbulence rather than in front. So this isn't the extreme condition, but I think it's a good example to show that uh, on a one-to-one basis, we can really have a very different result from Era 5. But we're just exploiting the fact that on average, Era 5 is somewhat correct. And I think on average, Era 5 is probably one of the best things that we have, which is why so many people use it. So we don't need it to be correct all the time. We just need it to be correct on average. So I hope those answers your questions.
Thank you very much for answering. Yeah, you touched all the key points. Just like you mean for the fluxes, it's very difficult. The EI5 probably sometimes missing the high and the low. Yeah, and one of the slides you should, I hope, still have time to ask questions. So not drag on. So, and I think one slide you showed the four seasons, and especially in the Southern Ocean, and you show those like sensible fluxes is downward, which is negative values. And I'm wondering, yes, that is the picture, and I'm wondering whether the leading flux and how was the leading flux behaved in this situation when your sensible flux is air is warmer and the ocean is cooler, so your sensible flux is downward, and in that case, what's the retrieval of the sensible flux, leading flux?
Yeah, so I on purpose didn't include the latent flux because I thought it looked relatively boring compared to the sensible. We have these very nice seasonal translations with the sensible. I have the latent. I can send it to you if you're interested.
Yeah,
But
I'd be right. I think even for us, it's sensible flux is easier to compute from the bulk, and the latent flux is harder, and we
yeah,
got very large unknown errors in this situation. So I will contact offline, and we have a new product. I'll be very happy to compare with yours.
that would be nice. Yeah. Just to show also that we have these, yeah, there's maps where we have these differences between Area 5 and at least for the southern ocean, for latent heat flux, we don't have these significant differences. So in fact, we have more differences
Oh,
for sensible heat flux. But
you you have probably the seasonal thing. You have a larger latent flux areas in the northern Pacific Ocean, and that is also area for larger sensible latent fluxes in our product. So
mm,
it's kind of, I don't know whether it cancel out in the South Ocean, but it showed up in the Northern Basin. It's the similar kind of error.
okay, interesting. Thank you.
Thank you.
Other questions? Well, I think we probably could keep asking a lot of questions. It's just a lot of excitement in here. And maybe I want to ask about, you're really just working from SAR, but you've sort of mentioned that there are other satellites. What are the prospects for integrating, say, sea surface temperature into this process? And would that make a
Yeah, so
difference?
that would in fact be one of the great things that Harmony could give because it has
Mhm.
this thermal imager. So that would be quite interesting. But
Mhm.
in fact, I would be more interested in when we have clouds, because then we would have this imager that can tell us information relating to the cloud structure, and the SAR could give us information relating to the bottom of the boundary layer. So we would have information relating to the top and the bottom simultaneously. And I think that could potentially be quite interesting, especially if you want to study the effect of large scale cloud controlling factors on your smaller scale phenomena. But that's in the future, so we don't have that yet. I'm not sure what, there's probably a whole bunch of matches we could make. For instance, we've also thought about using scatterometer winds to give
I
us
was
a
going to ask
good
about that. Yeah.
magnitude. But we're a bit unlucky, I think, with the collocations, at least for some of the scatterometers. So we haven't used those.
Is your orbit sun sync?
It's fixed, I think, 6 a.m. and p.m. local time.
Yeah. So you could use passive winds from WSFM. That would be the same time.
Okay, I'll try and remember that. Passive winds WSM. And
You could email me. I've got graphics to help on that one.
okay, but specifically for the temperatures, since we are able to apparently retrieve the temperature difference, it would be quite interesting then if we would have a measurement of temperature, we would immediately unlock the temperature on the other side of your interface. So if we have air temperature, we could get ocean temperature and vice versa. So, but that's, yeah, stuff we haven't looked into yet.
So we're coming to the end of the hour. If there are no other questions, I guess I want to make a plug for the next webinar, which I think will address one of your gaps. Megan Cronin is going to talk about Sunfleet and the prospects for in situ validation of satellite products. So thanks, everyone. Thank you, Owen, for a really great talk, stimulating discussion.
Thanks for having me, and thanks for all the questions.